Okay, I'm again recording and sharing screen. Success. So this is an awkward week because we're sort of reviewing for the first time, right? The past 7 weeks, except for the midterm, have just been, I'm going to barf all this math stuff at you that you need the rest of the week, so you'll have seen good example problems and had someone explain it to you. But now we're reviewing. And so we've already talked about unit analysis. You've seen this 5-step problem, not problem, process. You've seen example problems with it. You've done homework with it. So I'm going to instead go mostly through the book a bit and see how the textbook is wanting you to use it and make sure that all of that meshes well. I do want to briefly talk about the mad science measurement, just in case you care. Let's see what that is. And now by making the font bigger, it's not there. Okay, so if you want to do all 10 problems, then it's going to ask you to know about perimeter and area and what a polygon is. There's a bunch of polygons. Perimeter is walking around the edges, adding things up. And area is how many boxes does it take to fill up something? How many tiles does it take to put on the floor of my kitchen? So in this picture on the top, 2 times 4 is 8, so my answer is 8. The question is, what happens for other shapes? Where do these formulas come from? And if you were in Math 20, we would do this fun thing where I would pass out pieces of rectangular paper and we would go through this. But since you're not in person and we're not Math 20, then you don't get to have fun. I'm just going to tell you the answers. So how about this triangle with a nice straight up and down corner? This one is half of a rectangle. So how much of the original rectangle is the area? Half of it. So if we had the original rectangle and we called it base and height, the area formula for the triangle is half of base times height, because it takes half of that triangle. If you have just memorized before that the area of a triangle is half of base times height, now you know why, because it used to be a rectangle, but we cut away half of it. I'm cheating. What if there's a triangle that's not so nice? Here's kind of a generic triangle without a straight up and down side. Is this one also 1/2 base times height? Why would that be? You've probably memorized that it is. And the answer is that if I finish the rectangle, I can take one little flap and move it to the other side. And now you can see it is half of that overall shape. So this one is also half of the original rectangle, half of the original base times height. It just takes 2 steps. So now you can feel smart. It wasn't that 1/2 base times height was this weird magic formula given to Pythagoras when he went up on Mount Sinai. Now you can figure out why this works too. Parallelograms are flattened squares like an elephant sat on it. You might have memorized it's also base times height. Why is that true? And again, you can see with the picture, we could take the right-hand edge, make it like a little flap, cut it off if you actually had paper and scissors in front of you because you were in a Math 20 class, and make a base times height rectangle out of it. The tricky one, which I'm not going to tell you, but you can look for the hint, is the trapezoid formula. You have to photocopy the trapezoid and play with it to turn it into something we've just seen before. But you can actually derive the trapezoid formula for yourself if you want. And then if you were in Math 20, we'd look at these and just tell me the area of them without having to do any calculator math, just by using these formulas. Then we talk about metaphorical rectangles. If you have a kid in school lately, they've been taught this weird thing where instead of multiplying like this, like we were taught if you're an old fogey, then they multiply like that with a rectangle. Has anyone had their kids go through this sort of new math Common Core business?
In high school, I remember they taught us that, but it didn't make any sense when they taught us.
So Tangentially, if you actually read the original Common Core documents, they're great. There's nothing wrong with Common Core. It's just that when they got to be implementation and the fight for which curriculums and textbooks would be published, then things sort of fell apart a little. But now I'm getting into politics and I shouldn't. Anyway, so rectangles are useful. What you will care about if you have used that before is we can do the same thing with algebra. So if you're about to take an algebra class and you want to multiply x plus 5 by 3x plus 7, you can break it apart and have the 3x times the x in one corner, the 3x times the 5, the 7 times the x, the 7 times the 5, and when you get done with those 4 pieces, smash them all together. It's exactly the same thing as what we did with traditional multiplication, making different pieces and smashing them together, but with a picture. So if you're going into algebra, you might care about this. If not, I doubt it. And then we talk about circumference and area. If you were in front of me, I'd pass out pieces of string and you'd measure each other's arms and heads, but we're going to skip that for now. Read this and think about it if you want, and there we go. So the only unit analysis part are problems 1 through 4, as we mentioned on the to-do list for this week. The rest of it is kind of a weird problem for number 5, and then some geometry things for the last 5 problems. So if you want to try all of that, you can. If you're going into algebra, I would spend some time staring at this thing again. And if that's not helpful to you, you can skip all of this. Questions about that topic? Okay, that was way too fast, but I hesitate to spend more time on it since it is something that I don't think anyone cares about all of it. Let's look at the textbook then. So I'll go back to, now I have a question. If I share my screen in the textbook, because of my giant monitor, this looks very nice to me. I'm wondering if this is too hard to read to you though. It is too hard, I see nodding. Okay, so then I will close that and go to page 207 in here. Make that bigger. Share that. Okay, better? Yes, okay. Onward then. So more applications of dimensional analysis. We have our Jamboard, new shape, new page. We have a textbook. Let's see what happens. We're going to start by, for some unknown reason, talking about volume. I don't think that this textbook has talked about area and perimeter like we just did, sort of, already, but they're jumping all the way to volume, and that's okay. All you do is multiply things together. They talk about layers. You can think about, let me grab this picture. Okay, so if you're trying to find the volume of any shape, it's the area of the base times the height. And the best way to think about this is skyscrapers. Your shape will have some area of the base. The bottom layer has 8 units in it. We got this because it had a 4 and a 2, and 4 times 2 is 8. But this is not a 1-story skyscraper. It's a 3-story skyscraper. So there is also a 3 going up the side. So then we do That 8 times the 3 is 24 volume total. The 3 is 3 copies, 3 different floors of our skyscraper, 3 different 8s. Everyone with me so far? So they say length times width times height, but as a math person, I am not thinking about this quite the same way. In my mind, the length and the width are going together first to make the area of the bottom. And then the height is making copies. Of that area of the bottom. It's not that those are 3 equal things I'm putting together. Does that make sense the way I'm imagining it? Mathematically, they are, right? There's nothing special when you multiply 3 things. That means if I move on to a cylinder, then the same kind of thing is happening. What's the formula for the circle at the bottom? It's not just length times width anymore.
Pi r squared.
Pi r squared. And then when I'm done, I'm going to take this height and multiply that. So I take the area of the bottom and then multiply it by the height as a final step. So that way I can think about these two as the same process, even though the formulas are different. It's both the area fitting into there and then having the height go on after. Questions about this slide? Okay, if you didn't know the circle formula, let's go back and talk about that. What was I going to have you do if you were a Math 20 student with string? If I was to wrap a piece of string around a circle, and it's fun to use arms and heads because they're not circular, so it doesn't come out right, then the question is, how long a string does it take to go all the way around compared to the distance through? Or to put it another way, if you were to hold up a string to make it as long as from one side of your arm to another, how many copies of that string would it take to go all the way around the circle? Everyone okay with my question? If you were to try this with different vaguely circular things, the answer is about 3. And the more perfectly circular the item is, the closer it is to a certain number that's a little more than 3, it's a decimal. And that's just how circles work. So when we say that circumference equals pi times diameter, we are defining pi. This isn't something like the area of a triangle we just talked about, where we had to figure it out based on how triangles fit into rectangles. This is just defining things. I'm not sure, by the way, why we have the word circumference, because we already had the word perimeter, and that's a perfectly good word, the distance around a shape. And I'm not quite sure why we have the word diameter, because we already have the word width, and that's obviously the width of the circle. But people who like circles like fancy words, so there we go. So pi is about 3.14. You can memorize more digits if you want to show off. But the point of it is that if I was to take a string this long, it would take a little more than 3 copies of that string to go all the way around. And for most of human history, this was all we cared about for pi. If you were in construction, if you're making table legs or poles or pipes or something like that, and you wanted to make something circular, then you could either measure across and know that from that you could get the distance around, or you could wrap a string around something and know that from that you could get the distance across. Okay, so far?
Okay, so
Okay, but now we do, and here you can see this nice animated thing of, look, let's take circles and unroll them, and it takes a little more than 3 of how wide the circle is to get there. Okay, now this page is the next one that's important. This little brown square is r by r is size, so that's r squared, because r times r is what r squared means. And if I photocopy it and make 4 copies of it, then this shape here has an area of 4r squared. Right? We can count them. There's 1r squareds, 2r squareds, 3r squareds, 4r squareds. Everyone with me so far?
mhm.
So now I'm going to ask a strange question. If I have this picture, I'm now drawing the biggest circle I can fit in my shape. How big is this circle? And now you can see why I picked R, because that's the start in the middle and go to the edge of the circle. R is for radius. And the answer happens to be that the area of this circle well, it's clearly not as big as all 4, because these little wings stick out in the corners. But it looks like it's a lot more than half the circle. It looks sort of like it's 3/4 of the circle, more or less. And it just turns out that it's the same number pi, a little bit more than 3 of those r squareds that's covered up, which is wonderful news, because otherwise we would have to have 2 calculator buttons. One of them when we're finding the distance around circles, and the other one maybe a cake button for the area of circles. Why these 2 questions have the same answer is really profound and kept the ancient Greeks busy for generations. You can read about it elsewhere if you want, but for now, just be amazed. The answer to a distance around a circle question has the same answer as how many of these squares get covered by my circle, when you wouldn't necessarily think there would be any relationship between the answers to those 2 questions. So that's your area of a circle, pi times r squared, and how to think about it and remember it. Questions about that? No. Okay, so we're back to this. We can find the area of the bottom and then multiply it by the height. So there they go. There's an example of it. So Density is mass divided by volume. Okay, you can divide things. I don't think I need to spend too much time on this. I've given you harder things than that to do already. And now we get to see why they cared about this, because they're putting in some unit analysis. They're tossing volume and density at you as an excuse to do more unit analysis, which they call dimensional analysis because they're chemists. So they are using density as a rate. They had you play with density the previous few pages, finding some volumes, finding some mass, and doing the division yourself. But mostly they just want to say, here's the volume. Here's the density. It is a new kind of rate. We can cancel out volumes. The density is just a kind of rate. So I'm going to put that here too. And I'll be nice and call it dimensional analysis because they are. So last week you did different kinds of rates. You were converting feet to inches or minutes to hours or things like that. This is just a different thing you can use in the same process. And I suppose I should say that this is a volume. And this is a volume. This is a mass. By the way, imagine how big a centimeter is. Even if we are silly Americans that don't deal with centimeters much, you can picture a centimeter. If you made a cube, a little bigger or smaller than a sugar cube, smaller, that was 1 centimeter on each side. Everyone picturing that little cube made out of sugar or plastic or something, right? So this is sometimes called 1 cubic centimeter, because it is a cubic centimeter, right? That's what we just did. So cc is cubic centimeter. And sometimes this is called 1 milliliter. And I have no idea why people that are going to nursing or motorcycles use cubic centimeters and people that go into chemistry labs use milliliters. But they're the same thing. It's just 2 different words for a little box. Are there other things anyone can think of besides like motorcycle engines and nursing examples where people talk about cc's instead of milliliters? Okay, if you think of any, let me know. Okay, so sort of mission accomplished. We're now to unit analysis. You have example problems to mimic. You can handle this. There we go. Okay. There's a nice note here. Everyone know the difference between weight and mass? So mass is so much, how much stuff I have in me. Weight is how much gravity is pulling me. If I went to the moon, my mass would be the same, but my weight would be much less. My mother, who had a thyroid condition, used to have a t-shirt that said, "I'm not overweight, I'm just on the wrong planet." Okay, so here we go. Converting rates. You just used unit analysis. They're pretending that you're sort of new to dimensional analysis, so they're giving you more examples, but not great because they've taught this to you before. So there we go. And they're giving it to you in different examples of things, blah, 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 blah. And then they're giving you their metric system scoops. They go all the way to nano and pico. I'm not sure why. I've never heard nano or pico used in nursing, but I suppose the chemists might care about it. These are badly photoshopped pictures of fingers with fingernails. They're trying to draw decimal scoots, but it doesn't work well. Be nice to them, they tried. Okay. And then dosage, there's a bunch of abbreviations and things, and then more things to do unit analysis with. Molarity, they don't teach you molarity well. They talk about a mole a little bit, not enough really. They talk about molarity, just moles per liter, but you barely know what a mole is, and so on. So the angry chemist goes over this better. For now, you just do more unit analysis, mimic the problems. The angry chemist will help you understand what's going on. And that's all for chapter 7. Let me check my notes here. Okay, 8.3 and 8.4, I will skip to real quick. Okay, logarithms, they're saying, what is a logarithm? It says they are exponents. That's sort of true, but not really. I would think about them as decimal point scoots. The angry chemist tells you about that. The logarithm of 1,000 is 3. That means we have 3 decimal scoots, 1, 2, 3, to get from 1 to 1,000. And if you can't count to 3 just by looking at the scoots, you can plug it in a calculator, and there you go. Logarithms get a little more interesting when they're not powers of 10, because then you can't just look at the number and count the decimal scoots. What does it even mean to have the log of 212? It's not decimal scoots from 1 anymore. But there is sort of a pattern if you were to graph how logs behave, and you can put the numbers in between 1, 10, 100, 1,000, 10,000 on the pattern and do that. So your calculator should have a log key, and you can find your log key. Log of 212 and get some answer. So all they want you to do in the book is what I just did. Can you find your log key, plug in a number, and get an answer? So do that, because at the very least, you'll need to do that sometime else in whatever class is requiring Math 52, but there you go. Why you care about logs, this chapter doesn't tell you, because it's done. That was it. But you can plug things into calculators and then go read The Angry Chemist. 8.4 talks about pH. If you have a swimming pool or hot tub or something, fish tank, then you might need to look at pH. pH is a little confusing because it sort of measures things backwards. People are often told incorrectly that pH measures acidity, But the bigger the number, the less acidic it is. And that's kind of weird. You would think if it did measure acidity, then the bigger the number, the more acidic it would be, but it's backwards. And then there's a negative hiding in the log formula. So the angry chemist will explain all of that carefully, and you'll understand pH very nicely and make your future chemists happy. But again, all you were doing is saying, I'm taking this number, plugging it in the calculator, getting an answer. I am done. How do I plug this number in the calculator? 4.32 times 10 to the negative fifth. The Desmos calculator fails me. It doesn't have the right button for this. So I'm going to make a new slide and paste, coming to my rescue, the Windows 10 calculator. The number I want to put in is right here. I somehow want to put in my calculator 4.32 times 10 to the minus fifth. What does that even mean? Well, 10 to the minus fifth would be a 10 with 5 decimal scoots. To the left to make something smaller. The angry chemist will talk about that more. 1, 2, 3, 4, 5. So I could put the decimal point there instead and do that. But that is annoying. I instead want to just type it without having to do all of that. So what I can do is use this button right here. And you might have never noticed this button, or if you are like most students, you hate this button, because what you really want to do almost all the time is use your exponent button. And instead, there's this other button that you're not allowed to use because it gives you the wrong answer that says EXP and really looks like it should be exponent. Has anyone ever used this instead of that one by mistake? If you say no, I don't believe you. Anyway, so what that bad EXP button is about is what we are just doing. If I put into my calculator 4.32 EXP button, minus button, and then 5, and then equals, it will give out that long decimal I just showed you. Let me see if I can actually do that. I don't know if I've ever tried sharing screen with just the calculator. Okay, now you're looking at my calculator. So 4.32 EXP minus 5. Nope, it didn't do it that time. Let's try again. 4.32 EXP. I bet I have to go minus 5 that way. There we go. And why is it not doing 4.32? That's minus, no. Okay, my EXP button isn't working when I'm trying to show you things, which is embarrassing. So what the whole problem wants you to do then, pretend my calculator is working, hopefully yours will, is to do you're going to do a negative. Maybe that is a plus or minus. I bet it will be on yours. I'm going to change this minus to plus or minus. If you have one. plus or minus the log button. It should open up a parentheses for you. And then you would do this part, 3, 2. And then close parentheses, you probably have to do yourself, and then your equal to. That's your series of calculator pushes to do that kind of thing. Okay, without you watching, I'm going to try that again because why isn't it working? Okay, it looks like it's just because equal isn't working. Let me share my screen again. So what I want to do is the 4.32 exponent -5. And if I try and do times 1, then it knows what it's supposed to do. Oops, nope, I did it times itself because I hit the wrong thing. But see, it knows what it is. So what you want is a negative log. It doesn't want negative first. Okay, oh, I have to do log after. It's this kind of calculator. Okay, well then I will do log of that. So 4.32 exponent -5. Take the log of that, and then I get this -4.36. So to take the negative of it is just 4.36. Let me grab that. Put it back on our Jamboard. Okay, I sincerely hope you have a better calculator than the Windows 10 basic calculator. If not, we know what works. So that's all your new stuff for this week. And we're done 20 minutes early because I didn't actually do that many example problems of unit analysis. So I think we should go back and do more. So I'm going to stop sharing and pause, but not stop the recording. Your job is to go into the textbook and pick some example problems from your self-guided homework list for this week. Which ones do you want me to do from 7.1 through 7.4? And then I will do those. Okay, we are doing 23 and 7.1. A cylinder has a radius of 75 millimeters and a height of 135 millimeters. The density is this amount. What is the mass? Okay, so I'll draw a picture. There's my cylinder. I first need to find this area. So pi times 75. So what is that? Pi times 75 is about 236. Whoops, I forgot the squared. I'm bad. Times 75. There we go. 17,671. 601. Square millimeters. Then I need to multiply by the height. whatever that is. $2,385,000. $647. Now we're up to cubic millimeters. Everyone okay with what I've drawn so far?
Mhm.
Now things get a little tricky. This is a great one. I am glad somebody asked it. I'm going to start on the other side of my page. So I have 2,385,647 cubic millimeters. It's not a fraction yet, so I put it over 1. And I want to say how many cubic millimeters are in a cubic centimeter. And the cubic centimeter is what we just put CC for. So let's draw a little picture. If I have a box, do I get a box shape? And another box. Okay, pardon my bad artwork. There we go. So if I have 1 centimeter on each side, how many millimeters is that? Remember your decimal point, Scoots. 10, I see someone holding up fingers. So each of these I'm going to replace with 10 millimeters. So if I multiply, again, length times width times height, find the volume of this. 10 times 10 times 10 is going to be 1,000 cubic millimeters. So 1 cubic centimeter is 1,000 cubic millimeters. Everyone okay with my picture? If I was an amazing artist, then I would do something like a base 10 cube. See if I can very quickly find a picture. Yeah. You have to imagine that somehow my artwork skills are up to par with this kind of thing, right? Where there's 10 on each side. So because there's 10 on each side, you get to have 1,000 little cubes overall. But my artwork is not that good, so we are not going to watch that. Okay, so I can put that in. That 1 cubic centimeter is 1,000 cubic millimeters. If I multiply that, it's going to divide by 1,000. That's just going to be the decimal scoot 3 times this way. So this volume that I found in cubic millimeters, that was too small a measurement. Now I've changed it into cubic centimeters. And it turns out all I have to do is 3 scoops to the left, but hopefully you see why. These things cancel. Now I'm going to do a different either unit analysis. It wants me to use a proportion, whatever, but if I have, I'll do what it says, I'll use a proportion. So if it's generally true that we have 0.84 grams for 1 cubic centimeter, now how many grams do I have for 2,386 cubic centimeters? If you didn't like the proportion, you could also do this with unit analysis. You could also say that we had the 2,386 cubic centimeters, put that over 1, get rid of cubic centimeters, turn it into grams with the density, and keep going that way. So we're not done. Either you have to cross multiply and solve for y, or you do your unit analysis, multiply across top and bottom, do top divided by bottom, but you'll get the answer either way. When you're done, let's see what you get, 2,386. So we're going to take that and we're going to divide it by 1,000. Now I'm not rounding my answer. And then we're going to multiply by 0.84. So that's a lot of grams. I'm going to start a new slide to put this on. So however you did this, that's our grams.
Would
And
it be
whoever-
times 0.4 instead, or 0.84 instead of times 84?
Oh, yes, it is.
Oh, okay.
I noticed that my mouse clicking was bad. Thank you, thank you. There we go. That seems much more reasonable. Good job. Thank you for catching me. So still 2004 is a lot of grams. So what they're asking us next is convert this into pounds. Right. I'm a silly American. I'm used to thinking of weights in pounds instead of grams. So I take what I have, I'm going to round it. It's not a fraction, so I put it over 1. And I'm wondering how many grams are in a pound. I don't happen to know that. I assume the book told me that up above somewhere. If not, we can Google it. No, it's not up in the volume area. No. Okay, well, I'm going to use the fact that 1,000 grams is a kilogram, because that one I certainly know. And what I have memorized, I haven't memorized grams per pound, but I have memorized that there's kilograms to pound. Anyone else have memorized that? How many kilograms to pounds or pounds to kilograms?
1 kilogram is 2.2 pounds.
Yes. So kilogram goes on the bottom, so it will cancel. Okay, so grams will cancel, kilograms will cancel. So again, I'm going to unround my answer by going back to the calculator I'm going to take this answer, multiply it by 2.2, divide it by 1,000, and I get 3.7. That's a lot of work for an answer. Let me go back and review what we did. It started with a volume problem. That would have been a perfectly good problem on its own on the left-hand side of this page. Then we found an answer in an annoyingly small unit. A cubic millimeter would be this little bitty thing that would it would be small, even for a bead on a piece of jewelry. So we changed it into cubic centimeters, which people actually deal with. Then we did something, either this or that, to change it from a volume to a weight. That's what density does. And then once we had the weight, we said, I have no idea what 2004 grams is. Is that a lot? Is that a little? Let's change it into pounds, because that's something I know how to think about. Lots of steps. But for pretty much everything, it was just unit analysis. We could have unit analysis the whole thing in one long chain if we really wanted to be that kind of person. Okay, I'm going to stop the recording